Here we have a rotator that's spinning with constant omega, and inside of it is a small mass m in a frictionless tube, and the mass is connected to a spring with spring constant k, and the spring is fully relaxed at r equal to 0 inside the center. Let's analyze the motion of the mass if it's released at r0 from rest. We'll start with our free body diagram, in which case we have mg down and the normal up. We'll have a force P pushing in from the side. And we have a spring force here. And we know from Hooke's law F is minus kx. In our case, will be minus kr, since r is equal to x. We take a look in the r hat direction, which we'll define here. We'll define the theta hat direction in the same direction as omega is sweeping the end of this. We can look at the sum of the forces in the r, be m, a, r, and we'll get minus kr for the spring force equal to m r double dot minus r theta dot squared. And theta dot is omega. We divide through by m. We can combine these two terms and we'll get r double dot plus k on m minus omega squared. R is equal to 0. We're asked to look at this thing in terms of 3 modes of motion. And the 3 modes are driven by this term right here. Normally we just see the omega squared part here. But now we have a second term, this k on m value. There's 3 outcomes for this, if you think about it. This could be positive. It could be 0. Or this could be negative, depending on the strength of k on m and the value for omega squared. Let's take a look at the case where it's 0 first. For a 0 value, we see that k on m would have to equal omega squared. And at that point, r double dot would then be 0, which implies that there's no acceleration. So that tells us if it's initially at rest, it will stay at rest. Interestingly, if we were to integrate this, we could find r dot as some constant c1 and r as c1t plus c2. We'll recognize r dot is just v, so r dot would be some v0 if it had it, and r would be v0t plus r0. What this tells us is that without acceleration, if we were to push this mass and give it a velocity, it would continue to move at that velocity with constant speed until it exited the tube. And if we pushed it inward, interestingly, it would move inward with constant speed as well. It turns out for this case here that for k on m, r will equal r omega squared at all points r. So everywhere this mass moves, a sub c is increasing, and the spring force divided by the mass is increasing at just the right value to keep these two totally in equilibrium at all points. So we have an equilibrium event. And it's constant motion. If it's at rest, it'll stay at rest. If it's moving at 1 meter per second, it will keep on moving at 1 meter per second. The system is finely balanced. So case A, K on M equals omega squared, will have constant motion. R double dot equals 0. Next, let's take a look at the case where this term might be positive. We could call this U if we'd like. Just define that. We basically have R double dot plus U squared R is equal to 0. And we should recognize this as a classic sine cosine type solution where R is some A sine of omega t plus B cosine of omega t. R dot would be A omega cosine of omega t minus B omega sine of omega t. And R double dot would be minus A omega squared sine of omega t minus B omega squared cosine of omega t. So let's check it. We'll have negative A omega squared sine of omega t minus B omega squared cosine of omega t plus U squared and R, so we need that, A sine of omega t plus U squared B cosine of omega t is equal to 0. And looking at this, these two will drop if omega squared is equal to U squared, and these two will cancel if omega squared is equal to U squared. So this becomes our criteria for that. So it checks out. Next we need to find A and B, and we can do that with boundary conditions, which are that at t equal to 0, R was R0, and R dot was 0. It was released from rest. If we plug those in, cosine of 0 is 1, sine of 0 is 0, and we find that B is equal to R0. If we plug this into the velocity equation, sine of 0 is 0, cosine of 0 is 1, R dot was 0, we find that A is 0. So with that, we know our equation. So our solution will be that R is R0 cosine of omega, which is U, so this will be the square root of K on M minus omega squared t. And we recognize this as simple harmonic motion. This thing is going to oscillate. So our mass is going to oscillate back and forth while rotating with a modified spring constant. Recall for simple harmonic motion, x is A cosine of omega t, where omega is the natural angular frequency of the system. In our case, it's modified, so omega star will be the square root of K on M minus the omega rotational rate that system. So by having a spring rotate, it's modifying its spring constant in a sense. If we wanted to find the period of an oscillation, recall that t was 2 pi on omega, which would be 2 pi over the square root of k on m minus omega squared now. So here we have a modified angular frequency constant for a simple harmonic system. And if we look down here, it's decreasing this. So when we start to rotate this, it's going to have a longer period. As a result of it rotating. And you might ask, what happens if this becomes negative? We can't take the square root. Well, that would be a different solution. And that tells us that if we can't take this square root, this solution would not be valid for that condition. We'd have to look for something else. You could also ask, what happens if this was 0? Well, same problem. We get an infinite solution, so it doesn't oscillate at all. And again, we'd look for a different solution. That's one that we already solved. Now let's take a look at the third case, C, where it's negative. And for the case where it becomes negative, we have an interesting problem here, is that we're often taking square roots of this, and we can't take a square root of that negative number. So to deal with that, let's just rearrange this slightly. So we'll write it as r double dot minus omega squared minus k on m, r equal to 0. Now here we recognize this solution with the negative as a cosh and sinh solution. So let's solve this as r is equal to a cosh of pt. Where often I use omega here, but I don't want to use omega because I have it up there already and it'll just be confusing. Plus b sinh of pt. R dot will be a p sinh of pt plus b p cosh of pt, and r double dot will be a p squared cosh of pt plus b p squared sinh of pt. I think here you can see we plug this in to there, and we plug r into here. This will work if p squared is equal to that. So we find that p squared is equal to omega squared minus k on m, and we find that that becomes a valid solution if we use that for our guess of p up here. Now for the boundary conditions, they're the same ones. At t equal to 0, r was r0 and r dot was 0. We check that here. Cosh of 0 is 1. Sinh of 0 is 0. R dot was 0. So b is equal to 0, which takes care of that. And if we plug the second set in, cosh of 0 is 1. R initial was R0. So we find that A is equal to R0. And there we have our solution. So we'll get that R here is R0 cosh of omega square root of omega squared minus k on m t. And this motion we recognize, if we make a plot of it, cosh of 0 is 1. So it starts at r0. And for theta is equal to omega t, over time while it rotates, this thing takes off and goes to infinity. Right? So this axis would be r, and this would be r theta while it's rotating. And with that, we could calculate when it comes out of the tube at some given r, and so forth. Another way that we could have looked at this from the start is to recognize that that represents the acceleration along the tube. Right? There's more than one acceleration here. We have the acceleration along the tube, and we have our r omega squared centripetal acceleration as well. So this represents the change in motion along the tube length. So here, r double dot is 0. That would be constant motion. If this term is positive, when it comes to the other side, it becomes negative. So here, we would get a negative r double dot. And if this term were negative, when it comes over to here, it would be positive, and we would get a positive r double dot. Which, if we look up here, a positive r double dot tells us it's going to leave and move outward, and negative r double dot tells us that it would move inward, and a 0 tells us that it would stay right in that spot. So without having done all this analysis, we could have at least predicted the motion of this mass. What we wouldn't be able to predict was the sinusoidal nature of it, and in this case, the exponential nature of it leaving. Recall that hyperbolic cosines and sines are really just exponential functions, since that's equal to e to the theta. It's e to the minus theta over 2. And as theta gets bigger, that goes to 0, and it just becomes an exponential function going to infinity. So it leaves exponentially. Another way that we could have solved this, if we rearrange this, we could have done separation of variables on it, where we would have r double dot is equal to minus k on m minus omega squared r, and to save some writing, we can define this as n for now. So we'd have r double dot is equal to negative n r. We can define r double dot as dr dot dt and multiply and divide by dr. We recognize that to be r dot. So this is r dot dr dot dr, and if we substitute that into here, we will get r dot dr is minus nr, and we can multiply across by dr, and this is integratable. We'll get r dot squared over 2 is minus n r squared over 2 plus c, a constant of integration. And to find that, we look at our boundary conditions, which are that at r equal to r0, r dot was 0. So this is 0, and that's r0. So c1 is positive n, r0 over 2. And if we multiply through by 2 and collect these terms, we get that r dot squared is minus n r squared minus r0 squared. And if we plug in this value for n, and we get a final answer of r dot is the square root of minus k on m minus omega squared r squared minus r0 squared. Where that defines the speed VR along the track. And I kept it in this form because I want this to still be the same parameter we started with, where it can be positive, it could be 0, or it could be negative. If it's 0, the whole thing is 0, and we get that r dot is 0, it doesn't move. If it's positive, this is a negative, which means we couldn't take the square root of this unless r is less than r0, which tells us that this is valid when r is less than r0, so it has to be moving inward for that. If this term's negative, this negative out here will make this whole term positive, in which case then we have to ensure that r is greater than r0, and the object would move outward. The value, positive, negative, and 0, defines the domains where this equation would be valid. Thanks for watching.